All right. Internal, okay. MTF, this guy's down at 52%. Bad optics. No question, that's what we're trying to avoid today. Now, this wasn't due to standard LASIK. Don't misunderstand me. This was due to the non-recognition of dry eye before you did the LASIK. You don't ever want to do that. And what we do, I'll tell you a neat little test. It's kind of a neat trick. It's called a stare test. Terry O'Brien developed it at Johns Hopkins about 5 years ago, but it's real simple. If you take the smallest print a person can see, hold it right here, have them blink a couple of times and stare at it, that will blur on them in usually 8 or more seconds. If it blurs in shorter than 8 seconds, that's abnormal and they have dry eye. It's basically the patient's point of view of a tear breakup time. But the patient's much better because you're trying to determine whether it's breaking up over the pupil and where it's going, and they're looking at something and they'll tell you right then it blurs. And so that stare test, anybody that's over 10 seconds or is shorter than 10 seconds in our practice, measured the second time and gets plugged, but they've got to be over a 10-second stare test before they can have LASIK to make sure it's lubricated enough after surgery. And then there's a pretty good study out there that's showing that you get a little better reinnervation with Restasis, which is a product from Allergan. I have no financial interest, but it seems to help that better than anything else. All right, last one we'll look at today, minus 12. Now, you don't do 12 diopter LASIKs today very often. I do them rarely if you got a thick cornea and everything's just right. But there's no question that the more treatment that you do on the surface of the cornea, the more aberrations you induce. And up around 10 diopters, most people would agree that you're moving up into a zone that you're going to induce aberrations that were not there before the surgery, and the quality's beginning to be compromised. That's where my limit is, up around minus 10 or so. Some people draw that even sooner, around minus 8, but with wavefront guided, I do pretty good up around minus 10, but it's rare. All right, so let's look at this guy. Minus 12. All right, pretty good on topography. We got a pretty good zone here. Treatment's pretty good. Seems like a little hot spot down here, but we're on a quarter diopter scale, so I'm not too worried about quarter of a diopter of a little change in the cornea here, so we're on a real tight scale. Again, we look at the wavefront, and what we see is that same little area that was there at the Holladay OPD is showing up right here on the higher order and on the whole map, so we know that's topographic, basically. And that's what I'm saying. When you see something like that, if you were going to go back to do a retreatment on that patient, it'd be much better to do a topographic guided, which Nidek has because it's international, but it's not in the United States. So you couldn't do that, but what they call their CATs, computer topography or computed anatomy topography, actually does a good job. It does better than those. So when the problem's on the cornea, it's better to do a topographic guided, and if the problem's in the lens or the whole eye, well then it's okay to do a wavefront guided. Again, got some little lenticular changes, but what we see again is this guy's got bad optics compared to what the virgin eye would have to the green patient. He's performing at 40% of the performance of a normal eye. All right, that gives us just about everything we need to look at here. So questions? Questions? Yes, sir. Yeah, let me back up here and show you what, well, the only two lines that you care about, well, the D line is the diffraction limit. I'm trying to get them to take that off of there. Well, no, there's a D line, which is diffraction. The B line, which is the green line, is the normal. And then we've got ratios to B, which is all that count. We don't, I put these on there initially to show what the diffraction was, but look at that, 11%, because you're the diffraction. What we care about is A to B, 33%, and H to B, which is 32%, which is what the performance is to a perfect eye. The H is the higher order, and in this guy, all of his aberrations are higher order. Average for all aberrations. A is for all, H is for high. B is for best, and D is for diffraction. I don't know how that translates in Japanese, but that's what it is. Yes, sir.
Before you start that, we want to start comparing quality vision results objectively in our multifocals, crystalline.
Yes.
Should we be using the Straley ratio, the HB ratio, or the higher order wavefront?
for the quality, disregarding the refractive error, the best one is the H to B, area under the curve. The Strel ratio is not bad, but it's going to come up with a number that's never over 0.4, because it's not. Strel ratio is just like we do in those camera lenses, 100%. Well, the best an eye is going to be is 40 anyway, so you're starting off with a bar that's so low that it's hard to tell what's good, you see? Whereas if you start off with what we've talked about on the best MTF, well, then you're getting a value that's relative to the best human, not to the best camera lens.
What size pupil are you using for your corneal, or what size corneal aberration are you using? Are you using 6 or 8?
Well, now, that's a good question. Now, here's what happens. In Zernikeys, which is what we're talking about here, now remember, we don't have to go through Zernikeys to get these higher order maps. Now, we generate Zernikeys for you to select aspheric lenses, but we don't go through Zernikeys to calculate all this stuff because we got it in refraction in the first place. But if you're going to look at Zernikeys, then the higher the order, the better the resolution. So you put it as high as you can, which is 8th order. All right. The second thing is the size of the aperture is it's something that there's a click in there that you can put in the Stiles. You can't put in the Stiles-Crawford effect. So what's going to happen is when you select a 6mm aperture, the performance you're going to get for the eye is much worse than it's really going to be in real life, because the patient doesn't weigh those peripheral rays the same amount as an optical system. In other words, there's a Stiles-Crawford effect. 4.5mm pupil is the one that comes closest to performing the eye the way it's actually working. The problem with that is if the person has peripheral aberration and seeing halos at night, the bigger the aperture, the point spread function will show you the best of what that looks like to them. You see what I mean? So what happens is if I've got aberrations from a small optical zone, I got a big pupil. Well, I would go out in the light and I see fine. And I come in the dark and my pupil gets big. If you select a 4mm aperture, it's not going to show up. But if you select a 6, as big as it goes, then that'll show up as a reduction in the performance, and in the point spread function will show you what the patient sees at night. So the MTF says it's down, but the point spread function shows you what they see when they look at a headlight.
So I was asking about the corneal size for treating your spherical aberration.
6. Because the question was, when you're trying to figure out the spherical aberration in the cornea to select an aspheric IOL, all right, the lenses have been labeled over a 6mm zone because that's what we did in that original article. So in order to compare apples to apples, you got to select the same zone over the topography that was done originally in that original article. The Alcon lens, the WF is minus 0.15, the Technis is minus 0.27, and the B&L is 0. And those are over 6mm zones. So even if the patient has a 4.5mm pupil, you still have to talk about the 6mm zone in order to compare, because if you cut it down to, say the patient only has a 4mm pupil, well then the spherical aberration of the lens is not minus 0.27 for the Technis over that, it goes down by the 4th order. Well, that means that instead of 0.27, it's about minus 0.05. So you can't do that. So it's better to do 6mm with everything, and if then you don't, then what you know is you're going to end, you can't do it, basically, if you can't get a 6mm zone.
Would you add the 12th, 24th, and 40th term?
No, no. That's not, no. And I know Doug Coate wrote an article on that, and he's wrong. See, spherical aberration is an increase in power as you move out to the periphery. All right, that's the 4th order term. All right, it's a parabola. The next term up, the 6th order term, does this. It goes above that and goes below that. All right, that's the 6th order Zernike. It's got another little change in it. Well, you can't correct that with asphericity. You got to put another little thing like that on the IOL. So that little double hip that you get up there, you can't do that with the lens unless you put that on the intraocular lens, and you're not going to do that. So when you add that term in, it gets higher, but the intraocular lens can't correct that in the first place. The 8th order term does this. There's 2 blips in that thing. So spherical aberration is this, 2nd order or the 6th order is like this, and the 8th order is like this. So you're not going to put that out on the edge of the intraocular lens, so why would you want to add that to the RMS error to get a bigger number when it's not going to be corrected by the intraocular lens anyway? It's not going to help. because it can't do that unless you put a wave that does this out on the periphery of the lens, and nobody's going to do that. So no, you shouldn't add the higher order terms to the spherical aberration because the lens can't correct those. I talked to Lee Wang about that. I hadn't talked to Doug, but you just shouldn't do that. I mean, if you can measure that and add it, yeah, I'd add it out there. But you can't correct that second wiggle out there with it anyway, so why would you add that to the primary term, which is all you can correct with the lens? All right, how are we doing here? It's 5 and one more question, unless everybody's burned out. Well, I want to thank you for coming in for the last 10 minutes, Dr. Rosenthal. He got to hear the conclusions, and I want to thank all of you for being here for the whole time, and thank you so much for coming. Have a good day. All right, buddy.